giving me this opportunity to present my talk. And I'll introduce my talk today on energy transfer and localness or non-localness of the transfer. I wrote here dogma. Let me start with introduction of Kolmonov's idea, so-called K41. He assumes the existence of universality in the statistics of turbulence at sufficiently large base number and sufficiently small scale. And underlying this assumption is some idea expressed in this well-known poem by Richardson. Great, I don't know how to pronounce this, worlds have little worlds that feed on their velocity, and little worlds have lesser, sorry, my pronunciation is not worlds, and so on to viscosity. And Kolmov theory, so-called K41, is based on this idea and assumes the existence of universal equivalence range, and in particular in a sub-range. And behind this idea is so-called localness in the dynamics. And maybe this is a central idea of cascade. Cascade means this, large eddies drop down to smaller and smaller and smaller. And the distance is local. Dynamically, in expressing in not beautiful way, large eddies create a breakdown to small eddies, and small eddies create smaller and much smaller and smaller. And if this chain is long enough, then very small eddies forget what the ancestor did. Just something flowing determined this state. And small people forget long ago's ancestors' behavior. So they don't mind the detail of very large eddies. Just something very few determines the state of this one. However, one may consider also this kind of interaction. Very large eddies directly influence small eddies. Direct interaction. This is not direct. And in mathematical terms, if the velocity field is decomposed into large eddies and small eddies, then, as you well know, Navier-Stokes dynamics is nonlinear, bilinear. The convection term is symbolically written in this way. VV can be decomposed if we substitute this relation to this expression. Then this gives you interaction between large eddies and interaction between large and small and small. And the question is, which is the dominant, this one or this one? This is interaction between small eddies. This is interaction between large and small. And there are two ways of ideas. That is, if one assumes this is important more than this one, and if one neglects this term, it is just so-called rapid distortion approximation. Rapid distortion assumes this is not significant. One may drop this. And the idea of localness assumes this is important. That is, Kolmov's picture depends on this idea. This is local in scale. This interaction is local in scale. Small. This is small and very large. And the question is, which is dominant in deciding the energy transfer or energy? And additional comment here. We are considering about energy, not momentum. It's clear that in considering time dependence of momentum, the momentum equation is dominated by this term, not this term. This is for example, if U is constant, it's convection. The change of momentum is dominated by this term. It's clear. The question is regarding the energy, not the momentum. Because if this is constant, mean flow doesn't change energy. No deformation or no interaction can be represented by this term. If U is linear, just translating without change of form or no deformation. So this is often confused in literature. Scaling arguments, etc. There are many confusions in literature on momentum and energy. The question here is important is energy. The question for energy transfer, which is important, is my question. And recently, Julian Hunt proposed another point. Julian is a grandson of Richardson, or in-law. His relative, and Julian challenges Richardson's view by proposing this. Great worlds cover smaller worlds and feed on their velocity, but where great worlds grind, they also slow, and little worlds begin to grow, stretching out with high velocity up to the limit of viscosity. And if I borrow picture from Hokusai, this one, large eddies slightly go to small eddies. Now, my question is locality versus non-locality. Which is important? Locality in scale, not in space. To discuss the locality or non-locality of energy transfer, we need to define, we need some mathematical definition. So let me discuss some preliminaries. But we first need definition of energy transfer. We need to define energy transfer in a local sense. Function of x and k. I will explain later about x and k. What is x and k? And we need definition of locality or non-locality. In what sense we call it local or non-local? We need definitions. And I have to explain something about the interaction, nonlinear interaction in Navier-Stokes dynamics. That is triad interaction, so-called triad interaction. Let me explain something about this terminology. First, as well known, let's introduce decomposition to large and small scale components. For example, velocity fields or any physics field, quantity of physical interest can be decomposed in this way. This is, in terminology of large eddy simulation, this is called grid scale. And this is subgrid scale. For example, if you have this kind of signals, you can decompose this signal in this way. Grid scale and subgrid scale. By the way, this is the actual data, not cartoon. This is honest decomposition. This is from DNA data. And in spectral space, at low K mode, contribute to grid scale component. And high K mode, contribute to subgrid scale mode. This is rapidly fluctuating, rapidly in space. Rapidly fluctuating term, this is slowly varying grid scale. I call this grid scale and this subgrid scale. And in this figure, this is very small, but in terms of the number of modes, yes.
You are actually using Fourier filtering.
It at this point, it doesn't matter, whatever. Usually people use Gaussian spectral cut filter, yes, or Gaussian filter or something else. But in this figure, yes, this is subcut.
And what is the KC compared to your viscous key?
Whatever. At this point, we need not specify KC here. This can be moved. Whatever. So the or dynamics depends on Kc. Thank you. This is one of the key parameters. Here is for simplicity, let us confine ourselves to spectral cut. Spectral cut filter means this is sharp. Gaussian filter means this is Gaussian. For simplicity, this is very theoretically spectral cut filter is very good, very simple in thinking. However, in practice, this is maybe tricky because in real space, this introduces some maybe strange dependence on the position. So, but theoretically, this is very simple. So let's, yes.
Actually, this division large scale, subgrid scale. In subgrid scale, I can see some frequencies that are the same order of magnitude that are on the grid scale.
This space?
Yeah. Or it is a different scale.
Maybe in that case, perhaps this and this is not completely independent. Maybe some relation. But this is honest decomposition based on data.
So I think Fabio was having in mind that the amplitude of the two is comparable, and therefore there's no approximation. There's no approximation that you can do. You don't want to do an approximation. As
Maybe I was wrong. This was exaggerated. I don't know.
You mean it is?
In this case, this must be small. Conceptually, this must be small. But the answer depends on where is Kc. If Kc is around here, it's not surprising. This and this are same. But if it is here, you are right. This is too large. And I forget where was the Kc in this figure. So next, we need to define energy transfer as commented. The transfer depends on where the cutoff wave number Kc. And maybe we need to define energy transfer locally. Locally means depend on the position. And how to define? One of the natural definition of energy transfer as function of position and cutoff number Kc is like this one. That is, if we define Q as Q is the energy of grid scale, kinetic energy, Q, U bar U bar. Then, from the navigation we can derive some length equation. This is exact. And for SGS energy, defined this way, this one obeys this equation. And what is important here is same term T and T appears here. This is minus, this one plus. And what we may interpret this expression what T, here T is this one. This is like Reynolds stress. The structure of this one is very similar to Reynolds stress. So-called Reynolds stress in land modeling. This is definition. And S is rate of strength tensor of grid scale. And from these two equations, we can interpret T as energy lost in grid scale and gained in subgrid scale. That means energy at grid scale is transferred to subgrid scale energy.
But possible opposite process.
Yeah, it depends on sign. Thank you. But if energy is lost here, it will be gained here, and vice versa. If T is positive, it is lost and transferred to small scale. If it is negative, from small to large scale. Very important point.
But there could also be energy transfer through interaction with the mean flow. Is that actually captured by the T term?
Whatever flow is, this is just mathematical.
For example, an Acker effect. Acker effect, for example.
Yeah, but that should be governed by grid scale.
Right, but it should be explicitly in the upper
This is
equation.
exact, and whatever the mean flow, whatever may mean, this is exact, and just decompose grid and subgrid, and then manipulation.
I think in your case, for example, where T is the name, in your case,
I'll let you show you later. That's a very important question. And this definition have been used in many researches, but perhaps as far as I know, the origin of this idea is from Schreitman long ago. He considered the decomposition of fields into several bands. N means wave number band. Decompose the total contribution of all wave numbers into band. That is, wave number range are decomposed into bands. And this field is also decomposed in this way. And then total energy can be expressed in as a summation of band energies. And this is the exact relation derived from Navier-Stokes equation. And then this is the rate of transfer of proper energy density into all bands above n. Above n means some critical band and smaller band and larger band. Energy from crossing this band is expressed in this way. And this can be explained to be very similar to this structure.
And here, U bar, this is these regions outside of in a scale larger than subscript scales, yeah?
Yeah, U bar.
Okay.
And we have been in real space. Now we consider in wave number space. Then this is well-known energy equation. Energy spectra, dissipation by viscosity, and energy transfer due to nonlinear interaction. And by integrating this from 0 to Kc, we can derive this one. And this part is just average of Q. Q is grid energy. This is the exact relation. Then, in real space, from the Navier-Stokes equation, we can derive this equation, some length equation. But by comparing this we can derive this exact relation. That is, the average T is defined in this relation. The average means space average of T is this one, pi Kc. This is a spectral space representation. This is usually called written Tk in spectral formulation or spectrally. This is usually called W is called Tk. Anyway, this relation.
What is T? What is T?
C.
T is the transfer. T is
T.
No.
Kc.
Kc. What
Kc is the cutoff wave number. Sorry, this is Kc.
Very difficult to see.
Very dark.
Right. And it's for index C.
Yes,
Right.
yes. So, this is too large.
Yeah.
Now, by the way, some to note. In LES, people wish to model the turbulence in terms of only grid scale component by, in a sense, ignoring subgrid scale component. Then, that is, if we cannot accommodate all the modes, but we can treat only this part, then the question is how to represent the influence this mode onto this mode. We should model this influence. This is, suppose this is the exact Navier-Stokes equation. But since we are so poor and we can handle only limited number of modes, that is that PQK here should be up to some range. Then the question is how to model the influence of this part. And in spectral space, this kind of modeling is called larger distribution modeling in spectral sense. Then the question, most important question is how to express, that is the solid. This part is usually modeled as something eddy viscosity. Eddy viscosity, of course, depends on wave number k, as well as the position of cutoff number Kc. So the question is, if one accepts this form, then the question is how to estimate this term. Of course, this is a kind of cheating. This cannot be exactly correct. But once, if we accept this one, then we can estimate, in some sense, this quantity. That is, the process depends on the assumption. Okay, this is okay. Then, what is the best choice of this one? Then we can find this one. And it's not difficult. There are several ways to determine that one. But anyway,
the nu has a k dependence, and that means
and Kc
all these
would
higher.
be-
What I was asking earlier about artifact would in principle be included here. But of course, in order for that to be of interest, it should be a tensor. The u should be a tensor, a rank 4 tensor even.
Yes. In general,
Yeah.
this must be tensor. But in isolated turbulence, for simplicity, so in statistical sense.
MIMN. It is projection operator, some combination of projective operator. MI projector operator.
Which one?
MIMN.
Yes. This is yes. Yes, this is some expressing the influence of pressure and the tensorial dependence of the nonlinear coupling.
And turbulence K incompressible.
Yes. So, in symbolical notation, this idea can be applied to any dynamics governed by bilinear nonlinear. That is, including, if you include U here, velocity and B, magnetic field, symbolically, all are the same. And there's some theory, this is called, and this is from BNS data. It's possible to estimate the eddy viscosity. And what is interesting is that in the limit of small, this is the ratio of K over Kc. For small enough K, it must be constant. That is, this must be constant in the limit of small k as compared to Kc. So let's return to the.
That's what you plotted? You plotted nu as a function of k?
Yes.
It was the KC.
Yes, this is k over Kc. And Kc is in the so-called universal subrange.
I don't understand why it's first of all increasing towards high k.
There is reason.
What?
Later.
Where is the molecular mu in here?
Molecular viscosity is
No, I mean, in that plot, where will it be?
here.
No, I mean, in that plot, roughly where will it be? Compared to,
No, it's theoretically very much larger, different order, because nu is determined by epsilon, order of magnitude different. So scale in very high level number, nu is negligible in the inner subrange. If Kc is in inner subrange, this is much smaller than this one.
right, I just wanted to see in your plot where that is. That's all. In the plot.
Sorry, to simplify it. Yeah, as I said, this is K over Kc. This is normalized by some dimensional quantity determined by epsilon and K. So the normalization depends on epsilon.
Right, and in this plot, where will mu be? Much above, much below?
Nu,
Yes.
nu must be much smaller. In the limit
So it's not
of
even in the scale, okay?
yeah.
And how is it normalized? It's normalized with respect to RMS velocity and kf, yeah? Kc maybe even. So RMS is divided by Kc and 3
In
maybe?
the inner subrange.
Yeah.
And nu has nu turbulence is dimension of R
Yeah, okay, divided by K. That's what it
divided by
Sure.
K square or something.
Yeah,
Anyway,
yeah.
it is scaled by epsilon.
Yeah.
And
Yeah. So it's
Should be one, so that we are should be one.
yeah, right. You have the right So that will be actually
So
probably
this
really
can
fun.
be estimated using
But should be one source, right?
which one?
VR should be one source. No, first line.
First
Yeah,
line.
First line.
So energy is two-thirds.
Yes, VR. No.
So I
Like this. No.
Okay.
Okay, that's.
okay.
Increase of viscosity somehow suggests this hyperviscosity.
No. In the inertial subrange, this molecular viscosity doesn't play any role. Just energy flux epsilon determine everything. So one may forget nu. Nu is much smaller in the limited
Yeah,
wide
I'm
number.
talking about the defective one. This is growing, so somehow it suggests that the hyperviscosity is actually a good way.
No, sorry.
If
This
you-
is finite, not diverge. And in particular, this shape depends on the filtering. In spectral cut filtering, this has some cusp. If one uses Gaussian filtering, this is mild. And this is not finite, just order one difference.
You will
But
say more
just
about
increase,
this, yeah? You will say more about this, why it's
Yeah.
increasing, yeah?
Now, next, as I wrote some cartoon, people usually use this kind of cartoon, large to small, larger to small. This may introduce some confusion. This is not true in a strict sense, because in Navier-Stokes dynamics, the interaction is always coupling of two modes give rise another mode. That is, T plus Q give rise mode K. So always three wave number modes join to the game. It's impossible to write this way. It's not binary. Always to create mode K, we need always two other modes. So in that sense, the interaction is always triad. This is true also in MH determinant. And then, now we need to define what is local or non-local. And here are three wave numbers. And these three wave numbers magnitudes are similar in this case. But in this case, if we consider minimum of KPQ, this is minimum. And max is this one. And the ratio between this and this is much larger than 1. This is alpha, very large. And if alpha is order unity, it looks like this one. So intuitively, this kind of interaction is called local. This is called non-local. But this definition is not sufficient to define a local or non-locality. That is, and if one defines this alpha, parameter alpha, the energy transfer, the average of T can be written in this way. Here, I write here K, instead of Kc, I write here K. This is energy flux across wave number K. Can be written in this form. After some strange algebra, we can define W alpha. The question is, alpha means this localness parameter. And if the contribution to this transfer mainly comes from alpha order unity, then this transfer is dominated by local interaction. But if this contribution is mostly from very large alpha, then the transfer is maybe said to be dominated by distant interaction or non-local interaction. And this is a repetition. So the nature of this integrand, this determines the degree of localness of the contribution to transfer. So this is from data of DNS of moderate resolution. as you show this one. The peak contribution is about from alpha equal order 1 or 2 or 3. So this is decaying. And this is from long ago. I computed theoretically this contribution. And according to the analysis, the peak is from here. And most importantly, this integral, this decays in this way. That means for large enough alpha, this is very small. And most importantly, the integral converge. This integral converge. If this diverge, it is called non-local dominant. If this converge, converge means if we subset inner subrange scaling, and if this converge, then in the inner subrange, the transfer is dominated by local interaction. If it diverge, it is maybe called dominated by non-local interaction. This is the definition of localness or non-localness. But this is for this average.
So alpha has really it's really like an angle, right? It's not like a wave number, it's an angle.
Angle. In a sense, angle, generalized angle. And I heard, I haven't read the article, but according to Constantine, mathematician, I forgot, Peter Constantine, he told me he proved mathematically this one. So,
are there any suggestions in order to, are there any assumptions not to get this expression?
Very simply speaking, we assume the energy spectra is power law, maybe -5 third or something. And another assumption was perhaps epsilon, the transfer, is K independent.
K independent.
Constant flux. That is, if this goes this way, then nothing is lost and transfer. Independent of the K. That is so important assumption. Transfer is K independent. And energy or norm is bounded by algebraic. Then you got this one, according to Peter Constantine. And this is from spectral closure theory. And this and this agree.
So that theory from you basically is what Julian is saying.
Pardon?
Or your theory and Julian
Contradict.
Yeah.
I mean, maybe
For the moment.
Okay. I mean, maybe Julian was thinking about 2D or something.
No. That is my second story. Anyway, this is a temporary conclusion. Important point is if we have been considering about average of the energy transfer, phi k, is dominated by local interaction. This is my understanding. Perhaps I belong to minority. But this doesn't imply that large deviation statistics of pi is also dominated by local interaction. No local interaction may be important for large deviation is the topic of my second part of this talk. That is, we have been considering only average of t. But let me show you, okay, this is this one, t. As I said, t depends on wave number cutoff kc as well as position. So, for different position, t changes. And there are several studies on the statistics of this, and we have analyzed. This is a brief view of our DNA set. Let's skip. And as I said, t, the statistic of k, depends on where is the cutoff number. And I will show you some results for these points. That is, here is inner subrange. This is -5 third row. This is 4/5. This is dispersion range. KD dispersion. KI inner subrange. KE is energy continuum range. Please remember, KD dispersion, KI inner subrange, K energy continuum range. And here, PDF of T. First, before showing T, let's look epsilon. epsilon is energy dissipation. Epsilon must be positive everywhere. So the PDF epsilon is this one, positive definite or non-negative definite. And this is equivalent to well-known log normal distribution. This doesn't look like log normal because this is linear. If one plot this line by log epsilon, then this curve looks like this way, very close to log normal. So well-known log normal theory is very good in as approximation, but theoretically it cannot be correct as pointed by Mandelbrot. Anyway, this is epsilon, and green one is T for Kc to Ke, this one. And with increase of K, it becomes broader and broader. And next one is same data, but this is visualization. And your question, sorry. Average is about this is 5, this epsilon here. The average of this distribution is here. But what is striking is the deviation is very large as compared to the average. That is, average of this PDF is about here. But if I'm not sure. If T is T is negative, very large portion is negative, means it's called backscatter. Backscatter means energy transferred from small to large eddies, and it's not negligible portion. And of course, this portion depends on Kc, and it also depends on length number.
What kind of
Oh, sorry, this is K. Yeah.
What kind of what is it? It is steering force turbulence or
Oh, thank you. Yes. I skipped all. Okay. We used theoretical boundary condition, and energy, it's the force turbulence. The energy input was only at very low K, Kc less than 2.5 or so, and the maximum wave number here is about 2000 or 1000 that way. And anything else. We introduced negative viscosity at very low K, so as to keep the total energy constant during the run. So total energy is kept constant. So energy supplies at low K and go to high K and dissipated. So the energy is always constant.
So the ratio of the size of the force to the forcing scale is about 1000, yeah?
Yes, 1000 or 2000. No. More precisely speaking, this one, the data is here. Eta is the dissipation length scale, and L is energy containing eddy size. And the ratio L over eta is about at the largest. This is 4000 discrimination.
and L, what is it?
L is so-called integral scale, and it's okay. It represents the characteristic scale of energy containing eddies. And eta is the characteristic scale of dissipation. And what is important in this thing is that this backscatter, the probability of backscatter is very high, not negligible. And the deviation is much larger than the average. By the way, this is a visualization in real space. Red one is where the T is positive. Blue one is negative. Very large positive and very large. Sigma T is a standard deviation. And so this very high transfer region is red. Very low, very high backward transfer is blue. And we can observe that they are close to each other, adjacent to each other. And This is some quantitative analysis of the dependence of volume ratio of backscatter region is increased with Kc. That is, it's about 40% volume in the backscatter region.
The regions, this plot, the previous plot was interesting, and it looks perhaps familiar to people who have seen before a plot where you show the dissipation locally and the rate of strain locally, and they also are not in agreement, even though the averages are the same.
Yes, this is the point. This is epsilon. Epsilon r means average of the sphere of radius, and they are adjacent to each other, but of course they depend on the sphere radius or cutoff wave number. This one, this. And so this shows you there are some very intermittent,
Yes.
very calm region and active region.
Do they then actually also agree, you think? I mean, that the backscatter agrees with regions of where the local rate of strain is large?
Okay. This shows the relation between T and epsilon, and I will show you later epsilon and the stress and strain. No, vorticity. This one, yeah.
Yeah, what is it? Yeah.
This is the vorticity or entropy. On some plane.
Yeah.
That is, this figure shows you the only location, doesn't show you any intensity. This is show only location.
Yeah.
But this shows location, but only on a plane. And this is the height means intensity. And this is the dispersion. This is vorticity. They are very close to each other at a very similar position, but doesn't coincide exactly. We call it eddy shrimp. Tempura, do you know tempura? Tempura means eddy tempura means body of shrimp surrounded by dress. That is some strong vorticity region surrounded by dispersion range. It's like that. So next, and okay, Julian Hunt was much interested in this figure, and looking this, he thought that this kind of large deviation may be understood by this kind of figure. This figure suggests that this is total domain size. This is 100 liter.
I just had a question about this previous work then about the backscatter forward scatter.
This one?
Well, just in general bit.
Yeah.
Do you know something about when if you talk about backscatter forward scatter about the localness, non-localness? I guess in backscatter is much more local than forward scatter. But I'm not sure.
I'm not sure, I don't know. So we need some conditional statistics.
Yeah.
Yes, that's the next topic. This is the analysis of average of T is only global average, non-conditional statistics. Now we need to think about conditional statistics.
Yeah.
And as a first step, this figure suggests that in some region, as I said, this is very calm. In some region, it's very active. And this one. Here maybe Julian considers this as a belt or a layer. Very long structure with very small spikes, very high. And here is some interface of active and non-active region. Now, we can observe in many flows, interface between turbulent and non-turbulent flows. This is from experiment, turbulent boundary layer. Here is the voltage. This is potential flow field. This is mixing layer, a turbulent jet in a laboratory experiment. Here is DNS result. Turbulent boundary layer. The eddies are confined to close to walls. Here is the turbulent mixing layer. There is some very dense region of vorticity, and this part is potential flow, no vorticity, and there is some sharp interfaces. This is image and technology. This is Sakurajima. This is locomotive. Can you see? There is very sharp boundary, some particular shape. Not this way. Why? I don't know the boundary this way. Why it is always this way? Not this way. Why? Always.
Growing,
Yeah. Always some curves are put. Okay, anyway. This is the analysis. Again, oxide. Now, return to this picture. This is interface in turbulence itself. Not turbulent, turbulent, non-turbulent interface. This is within turbulence. So, even in homogeneous turbulence, there may be sharp interface between calm, I call this non-turbulent, and active, I call this turbulent region interface. And this is a signal along a line, velocity, very intermittent. And this jump is order 1, normalized by RMS value. This very big jump occurs in very sharp layer. By the way, I didn't bring the visualization suggests the turbulent field consists of tube-like eddies, and each tube has diameter. The waist is about 10 eta, and 300 eta is approximately 4 lambda. So lambda is so-called Taylor microscale, and the layer, approximately speaking, this size is L. This is lambda, and this peak is about 10 eta. And the data here is too large, so we divided the total domain into small boxes, and we pick up one of the boxes from many. Each box has this size. So about 64 by 8 boxes we prepared, and among so many boxes, we picked one box that is here. The box must include some active region. And this is another, the same box, but with some coarse-grained filtering. Anyway, let's skip. And if we introduce some cut here, this plane, then plot the vorticity or entropy, looks like this one. Again, here is some layer-like structure, and here is some interface. That is, active region has some interface, and here something very active is occurring. And we introduce a conditional sampling. We define this interface in some way and plot statics as a function of distance from this interface. And then, anyway, this is some technical detail. Then here is the vorticity in some direction, and suddenly change across the interface. This is right-hand interface. This is left-hand side interface. Anyway, from up to this point, in turbulence, there are some active regions, and this scale is very large, and this scale is about order lambda, and here is very sharp interface. And then, as we introduce some cutoff here and analyze conditional statistics of energy transfer for these two values of it. Here K is KC, cutoff of number. And then the PDF is this one, very similar. This is in total domain. This is in the, I forgot, in a very similar. Conditional statistics and total statistics are very similar. This is, can you see? This is distribution of dissipation, and this is entropy. And after filtering, cutoff filtering, this is TK, for K, small k, this is large K. The distribution of transfer looks like this, and here this is layer. In the layer range, C is large. And this is this distribution of energy transfer. Conditional average as a function of distance from the left interface. This is as a function of distance from right interface. So in the layer, this is layer range. In the layer, T is very high. And the boundary is on the left-hand side is sharp as compared to the right one. And we plotted PDF. This is in total range. And this is in the shear layer. The red one is shear layer. This is near layer. And so the PDF is much wider in the shear layer.
Shear is in a region where vorticity is very strong?
Yeah. This is called shear layer.
Yeah.
And overall, it's total video. This is conditional statistics focused on shear layer.
Are these still integrable? Is the statistics still integrable? I mean, can you get an RMS velocity still for these? For the active region, you say have these very shallow PDFs, right?
This one. Yeah,
both the red one in particular, right?
Yeah.
And
this is T normalized by epsilon.
Yes.
Epsilon is average over the range.
Right. And you see average and converged.
Then the same data was plotted against. This is normalization is epsilon within the layer. Then the shape is very thin. That is dissipation. Here is active region, and epsilon in here, epsilon outside. This is much large. Epsilon is much large. So if one normalizes T with this one, and T this one, then the shape is very similar.
All right. Yeah.
This is the distribution of transfer. But my main interest was localness or non-localness. I'm not answering your question directly. You once asked about the back transfer and forward transfer, but we are considering about the conditional statics using a layer. And it was, in a sense, very complicated to define the localness parameter W alpha depending on the position. But some tedious work, we can formulate this as a function of x. That is, I wish to know the localness of energy transfer in this region or outside region and compare. That is, energy transfer may be I suspected energy transfer in this range may be very non-local, and this contributes much to the large deviation. Large deviation statistics may be dominated by this kind of very big change or shear layer, and in that range, non-local interaction may be very important because shear is very strong and large-scale structure, and small-scale structure may directly coupled to this large-scale motion. So I suspected the nature of interaction may be different in this region. So I tried to analyze this one. So I have not reached any conclusion, but let me show you some tentative results. The answer is this one. This is alpha. Oh, this is alpha. This is overall average. This is condition. There are several conditions, that is within layer, near layer, over total range. And in the shear layer, shear region, the peak shift large alpha and upward. But the slope for large alpha, when you plot long plot, the slope is very similar. So in a sense, I suspected that this slope in total range and shear layer may be different, but this result is not very conclusive because there are many problems in this analysis. Skip this. That is, this is not. In the shear layer, transfer is very high. PDFT is broader, and W alpha is larger. It's non-local, it's stronger. But the question is, first, our code is correct. We should check the analysis. And this is very strongly anisotropic structure, but we introduce some isotropic operation. So the analysis may be not very good for obtaining condition statistics of this kind of strongly anisotropic structure.
Non-locality is most strong in the vicinity of the regions with a high elasticity. Yeah?
You're suspecting, you don't show that.
Yeah. But comparison shows it is stronger than the other areas. But you said most strong or not? Is there any other place which is higher? I don't know. We just analyze one place. So this is an ongoing study and no conclusion yet. But anyway, there are some very sharply changing regions, and it may contribute much to the large deviation statistics. And Julian suspects this kind of shear layer is important in determining the statistics. And another conjecture is, in that region, non-local interaction is important. I don't know. So this is just an informal seminar and conclusion.
Thank you very much.
As I know, Julian likes rapid distortion theory.
Yes.
Is it an example of non-locality?
The use of rapid distortion preassumes the importance of non-local interaction. That is, rapid distortion ignore local interaction. That is
Local, okay.
Local,
No,
yeah.
not totally non-local. Okay.
Yes.
Okay. So I understand now.
That's a neutral theory, essentially.
Yes. That is
No.
exactly.
It means
U plus U prime. And this term is ignored in rapid distortion.
so you no linear.
So
It's
this
okay.
preassumes.
Right.
It is pre-requirement that this is small.
But it's more complicated than so, because you large number, you more, you don't.
In K41, this must be essential. The interaction with this one.
Look.
Non-linear is important. And rapid distortion challenge that idea. Rapid distortion means linear term is important.
So you said that you suspect that when velocity is high, non-locality is stronger. But
Only conjecture, I don't know.
but could it be that so in the end the cascade is non-local behavior, even if you want to quantify how much non-local it is.
Yes.
So it could be that when the vorticity is higher, the energy transfer is more efficient, and so you see this cascade on a shorter time scale, or not. I don't know if you see what I mean.
This kind of argument based on vorticity often result in confusion. For example, it says, like in Facebook, any regions broke down to small region and then this kind of breakdown process is often used. However, if here is vortex line, and if it is stretched, that is, there's no object like this one. Always the vortex cannot end within fluid. So if it is elongated in some direction, for example, the conservation of circulation means if this is stretched in this direction, this must be shrink. Then is this backward or forward? Or if the vortex thing is stretched in some way, then this becomes smaller. So the scale of edge is very vague idea. So I need mathematical definition of strength of interaction. This is, in a sense, very bad idea, very intuitively understandable, but this cannot happen in reality.
Yeah. So there is no, in some sense, so there is no any connections between cascade and vorticity dynamics in some sense. Yeah, is it true?
Not all.
It's a very challenging statement. It offends many people. Many people like to understand cascade or transfer in terms of vortex dynamics. That is, usually it says vortex stretching. It's strange. Vortex stretching means that this becomes small, and so large scale motion is squeezed and size decreased. However, stretching means elongation. Elongation means generating large structure. It's confusing.
But maybe it means in some direction small scale and not the large scale.
The conservation of vorticity always implies stretching and constriction. It's strange. Why can't you use energy transfer? In some sorts, the breakdown must be involved. Breakdown and to dissipation. This was pointed by Professor Kreitner. If you consider some vortex line, how can it be, the energy can be transferred by this kind of dynamics?
But in the end, the stability of this stretched vortex is, this stretched vortex is less stable than the.
It introduces something else. Stability, yes. So stability means, in a sense, linearization. U plus U, and ignore this U square. Implicitly it assumes something non-local already.
So why was the U of k increasing the scale?
Pardon?
Why? I think I missed at least the answer. U of k was first flat, but was increasing by a factor of 3 perhaps.
Yeah.
And not decreasing.
It's easy. I mean, this is E, Ek, and it runs this cutoff. Then, the increase of U means energy transfer. This is larger than this one, simply. Or, if you are fixing K here, K, that is, local interaction is more dominant than local one. That is, K,
So maybe you're saying it's subdominant at
This
at small
one,
k.
yeah, this is Kc. Here is no K. And the contributions are from this one. Oh, no. Yeah. No K, Kc is in a sense contribution to this flux. And this is smaller than this one.
Yeah.
And increasing, if K approach this boundary, the contribution is increasing.
Maybe that's what I was thinking, because I was thinking probably beyond Kc. And for K,
But in areas we confine only in this range.
yes.
But if you decrease Kc, so turbulent viscosity will increase. Yeah? Because
Here we confine only in the inertial subrange.
yeah,
There
I mean
are
inertial subrange. Yeah.
some scaling and some similarity is assumed.
For example, if we apply some kind of renormalization growth theory, which is in some sense similar to the large eddy simulations.
Yes.
Just
Yes.
you average up to the some scale, then you increase scale of averaging. Then in such a way you can derive equation
Yes.
for turbulent viscosity
Yes.
as a function of scale.
Yes. The best kind is very common, but the process of renormalization group theory includes many questionable or doubtful
Yeah,
process.
of course.
It's
No
very
doubt.
difficult. That is another problem is that in Yak potential theory of renormalization group, assume non-locality is important. That is, if non-locality is important, then we can introduce expansion in terms of this. That is, for this, if, anyway, that is scale separation. If one can assume scale separation, then we can get some parameter, the ratio between this scale and this ratio. Then we can do this expansion in terms of that small parameter. Then the solution is very happy. But unfortunately, this parameter is order unity.
Yes,
So the
exactly.
expansion break up. So that's the main difficulty of Osaka Airport scheme.
When you were assuming isotropy throughout, that of course is valid globally, but once you are dealing with structures like this, certainly this isotropy assumption must break down, and you should really have
That's another point of interest. That each eddies have this kind of strong ion anisotropy. This is banana, not apple. But banana distributed randomly, isotropy, then statistics is isotropic. So each element is strongly anisotropic, but statistics can be isotropic. And after averaging, for the average, we can safely assume it's isotropic.
I think that's exactly the difference between a fluctuating alpha effect and assuming no
Yeah.
alpha effect at all.
But if there is some particular direction,
It matters.
then yes.
I'm not sure. I mean, even if everything is random globally, I think it might matter actually.
Yeah. And in our
Depends on how it appears in the equations we are trying to write down.
Yeah, we know. There should be things like an archive effect, for example, and other things. And that effect.
And perhaps the similar analysis for energy turbulence gives you no locality is dominant.
Right.
Easy? Yeah.
But if you
Sorry.
usually in high dynamic turbulence with high Reynolds number, if even in a larger scale you have anisotropy, but if you decrease of scale, you anisotropy will be decreased strongly.
Thank you. It's another interesting point. The famous one is 4/5 law,
Yeah.
by which we can predict exactly this is 4/5 fictional R. Under the assumption of stationarity, homogeneity, and isotropy. And K41 assume, as you said, with decrease of scale, anisotropy also decrease. However, nobody knows how fast that decrease is. And according to our data analysis, it decays anisotropy factor, say, decrease some power, very simple power.
Uh-huh.
No theoretical prediction about this.
Mhm.
So, asymptotically, for a large enough number, deep in inertial subrange, then anisotropy is okay. Anisotropy decreases, but only algebraically.
Mhm.
So in a sense, very slow.
Ah, very small, okay.
What do you call active regions? Is there actually a theory for that, or is that do you take it simply for granted that you have these large clusters?
Yeah. We measure entropy as a position or as a function of position, and we call active region if this
Yes.
is some threshold value.
Yes.
Then we
Right.
call
Yeah, and,
this
these
one.
have, and the point is these regions have large scale. They encompass many eddy scales, right?
Sometimes in one direction, but not in the other.
No, entropy is not.
Oh, right, you're not talking about energy dissipation,
No, sorry.
So
Sorry.
the question is really, have somebody asked why you actually have these conglomerates of, what is the, all of a sudden?
This one. This plots dissipation and
Yes.
entropy. Entropy is not doesn't have any particular direction. It is some of the scales in each direction. And we call this region active if this is higher than some threshold.
Yeah.
But if you try to see distribution of energy of turbulence, energy will be localized inside these active regions, so it's difficult to say. For example, recent theories by Gurevich and others suggested that main energy of turbulence is concentrated inside the vorticity regions, inside the regions with high vorticity. But you don't observe this in direct.
We didn't measure, no. We have some data for measurement of energy, but we didn't pay much attention to that because generally it is really the statistics of velocity and vorticity are independent. And in particular, consider this kind of vortex tube.
Yes.
Translating without change of form very rapidly or very slowly. And this energy is very large. Translation. This is slowly. But velocity is not Gaussian invariant. It depends on the coordinate frame of the chosen. So we assume the vortex dynamics is independent from the choice of observation coordinate. If it is translated by a very large flow, it doesn't change any energy.
Finally, what about this one here? Did you find the answer? No?
This is very interesting. For why you don't observe this?
What's the answer? Question is open.
Do you know the answer of this? Why this doesn't occur? Ordinarily, you observe this.
I think we know answer why it's so sharp. But it's why it's pillow-like and not opposite. It's all. What is so sharp? I hope we can explain.
I mean, it's a bit like the G equation solution, yeah? Can you apply the G equation to this thing?
What?
The G equation for turbulent combustion, you have the equation for front propagation. And I think that if you can actually apply that equation, it will always have
But
these.
isn't it for
But you need
distribution?
Did you have it from?
Isn't it because isn't it due to distribution? Because when you
No, okay.
concentrated smoke, for example, there, and then it diffused outwards.
No, diffusion is due to slope.
Important is that
Is right.
in these figures, what you are observing is, in a sense, passive scalar convected by flows or fluid motion. Here, no. What is plotted is vorticity, not passive scalar.
Yeah.
So there is subtle difference between the interface of vorticities and interface of scalar passive scalars.
Yeah, in some sense,
And they may be different, or but very similar. Both shows this one. So it implies vortex is convected by some mechanism similar to that of passive scalar convection.
But in some sense, analogy between vorticity and passive scalar equation is not complete because vorticity is a curve of U.
Yeah, I agree. But still, very similar.
Yeah.
So, one, perhaps some Stanley Corson, I don't know how to pronounce it. Corson.
Yeah.
Corson discussed this, and that is, vorticity is convected by something, but the point is why the boundary is sharp. And how does the structure of this sharp change? We have some suite with very thin skin. What is the structure of the skin? What is the depth here? And why here is skin? The skin means protection from some thing from outside. There must be some mechanism to keep this skin. Perhaps.
I think it's like which kind of gas contain more energy. Because you can imagine a smoky room, and then you put a jet of clean air, then you will probably see the opposite effect. So it's because smoke contains more energy, which gives you a better time.
But generically, there are many similarities between many phenomena, and there must be some common feature.
But then the propagation direction will also be the other way around. I mean, here the whole front is propagating in this direction. Right? That's the overall propagation of the front. Now, in your example, would that actually...
Okay.
Would it be like this, something?
No, so it's always continuing.
Yeah, right, exactly, yes.
Okay. First time, difficult to fit it plus this minus argument, but in this kind of mixing medium, this is front or combustion or reaction or detonation, some wavy surface may appear. In that case, it's difficult to tell this kind of story. But again, there are some sharp changes, and this interface protects something. Disturbance cannot enter directly to that region. In some case, I don't know. Anyway, there are many things I don't know. I don't understand.
Okay, that sounds like an idea to discuss further things over coffee, which we can do now. I forgot to say that there's also the flow seminar tomorrow morning at KTH, 10:30. And the topic of that, Gerd, can you remind us again? Is the topic something which is different from today and tomorrow?
Well, I don't remember the third one.
I plan to talk about anisotropy due to some disturbance, shear or some external function. The inner subrange should be deformed in response to the disturbance. And in my understanding, it represents also some kind of universality, like some so-called linear response theory or fluctuation dissipation theorem. That means some equilibrium system, when it is disturbed by some external function, it responds in some way. For example, if you impose density gradient, then there must appear some current, density current, in response to the gradient. Or if you impose electric electric field, then there must be some electric current in response to this imposed external field. Then if you impose shear to equilibrium state of case 41, then this should respond in some universal way. That is my interest, so I will talk about that tomorrow. That is linear response theory of turbulence.
But in a linear response, you have a temperature.
Temperature.
In standard linear response, we are basically thinking about slight deviation from an equilibrium system, which is in a particular temperature.
So,
and temperature plays an important role.
yes, yes.
So
And
in terms
in
of
turbulence,
turbulence,
yeah, in turbulence we don't know anything about like Hamiltonian or Maxwell or Gibbs distribution. We don't know temperature. What is the degree of turbulence? We don't know. But still, if we assume existence of equilibrium, then we can apply some formulation and then predict something.
you don't mean equilibrium, right? You mean at unit station.
Not necessarily, just assume something, existence of something.
Yes.
Then if you apply something, then the response must characterize this state. That is, my favorite analysis will be like this one. Here is a watermelon, suppose. And if you wish to know if this is sweet or not, watermelon is sweet, fruit. If you have given some fruits, and if you are not allowed to cut, but if you wish to know if this is sweet enough, what you can do is knock and listen to the response or sound. If the sound is correct, good, then this must be sweet. Detecting some response gives you some information of this internal state. So this idea can be applied, I hope, to turbulence. We don't know exactly what is this state is, but if you apply something, you must get something, some information, and from that we can know something.
So if people have particular things to discuss with Yukio, I suggest you hang out here and grab yourself a coffee. That's what lots of us will do. But before doing that, let's thank Yukio again for